of amplifiers are there, CBC, and so many types. Today I am explaining you mainly we are using the signal amplifier as a C configuration. Okay, so these are the given values. These are design given values in a data sheet. Okay, or we can define our values. Let's say VCE. That VCE means let's say voltage between a director to amplifier. Okay, and then this is my load current. This is my amplification factor. Okay, so for design we want to assume few of the points in an amplifier stage. Okay, that's the first assumption is that the base emitter voltage is voltage plus the 0.7 volts. That's the first assumption. As we know that, right? That's the diode. Its potential is 0.7. Okay, and then second assumption is V. That V is a 10% of VCC. That's a design value. Okay, and then the third assumption is a IE. My IE, that means, this is the current. IE is a emitter current. This IE, this should be equal to the IC plus IE. Okay, that's the formula actually. IE is equal to IC plus IE. But we want to neglect this IE. Why we want to neglect IE is, we know that like the base current of the transistor is very small. In terms of the milliampere is a microampere. So that's why we neglect this. Okay, let's come back to the design. So that given value is okay. We have one assumption too. We can define the V voltage, right? That's this voltage. V. So from this we can I almost from third assumption I is almost equal to IC. Okay, that is equals to 1 volts divided by 2 milliampere. So that makes sense 500. But there is a case in a practical way. There is no 500 ohm available in a practical case. That's why we are using this for some ohm. Either or you can use as a 30 ohm plus 180 ohm series current. You can get appropriate values. Okay. So and the second resistor is a load resistor. This resistor is called as a feedback resistor. That I am going to explain you in a later session of my session. That means when I take this negative feedback and positive feedback, there I explain you what the necessity of having this resistor. Okay. And then this is a RC resistor. That means this resistance. This is a load resistance. Actually, we call it as a load resistance. So, except external load, there should be load with the transistor. That means amplifier. There is a load. Okay. How can we design that load? Means, okay, let's apply a KVL. What is a KVL? That's a total loop voltage must be equal to 0. Okay. That's this is my source. VCC. Then IC into RC. Let me write a KVL equation for that. Okay, VCC minus IC RC, then minus VCE minus VCE. That's equals to 0. This is a KVL. From this we can extract RC. So VCC minus VCE minus VCE. We know that VCC, right? That's a given value. And VCE also the given value. So by 10 minus 5 minus plus we already defined in assumption 2. Okay. From the divided by IC, that we get 2 kilo. But there is a practical case. There is not 2 kilo, right? That's how we gonna use 2.2 kilo. Okay. That's my load resistance. Okay. What about the biasing resistance? Oh, these are R1 and R2. These two resistors are called biasing resistor. We want to bias our transistor, that means our amplifier in a certain activation, right? These two resistors are bias our amplifier. Okay, let's we design the resistor. Okay, that's a beta. This is my one of the assumption. It's not an assumption exactly, it's a design itself. Okay, beta into RE, that should be greater than the 10 times of RE. That's it. Given specification. Okay. And that should be R2 is less than beta RE by 10. And of course the RE value, R2 value is in a given. That means it's a normally practical case we will use less than 5 kilo. That's why I taken it as a less than 5 kilo. Okay, that is equals to and then VR1, this is that VR1. So that VR1 was sure. This R2 I designed is beta is a 100. Okay, so I'm gonna write 100 and RE is what the RE design value. Okay, RE is where is RE? This is a 470. Okay, and then this is a 2 milli. Right? No, it's a 10. That's it. Okay. Of course, this defines up to 4.7 kilometers. Okay, you know that, right? That's a less than 5 kilometers, of course. Okay, that's a VR2. What about VR1? So, VR1 we can define that. VR1 voltage, this is the voltage divider, right? Except this. Let me take this. This is a voltage divider, right? Okay, that's a VR1 and then the VR1 is equals to VCC minus VR2, right? Yeah, sure. Okay, let's combine this. What is the VCC is a 10 volts, V2 is a 1.7. Yeah, that's VR1 is getting by VCC minus V2. That VT is this voltage. This is VT. How do we get this VT? Yeah, that's a VPE plus V. Yeah, that's it. Okay, you can write V2 is equal to VPE plus VT. Also, that's a V. We know that that's a VT is a 0.7 volts. That's our first assumption. And a V is a how much? That's a 1 volt. That's our second assumption. So then, what's the voltage? That's a V2 is a 1.7, right? 0.7 and 1 volts is a 1.7. Yeah, that's it. 10 minus 1.7 is a 8.3. Okay, let's come back to one more analysis and assumption. It's like assumption. Okay, that's the R1. That means this current flowing through R1 is almost equals to R. Why means we are neglecting this IV. I told before, IV is in terms of microampere. That's why we are neglecting this. Okay, let's assume there is a current flowing means current. 10 times flows in a R2, so 1 time flows in a I. So that means base. So we are getting for the analysis purpose and practical purpose we are getting I. Okay, let's come back this. That means our IP is 1.7 volts. This voltage is potential, and then that's the resistance is equals to that's a 22.9 kilo. But there is no problem with that. There is no 22.9 kilo. So we just use as a 20 kilo. Okay, let's come back to what's the XC. So, this capacitor. This capacitor is called bypass capacitor. Why we use this in a circuit means we have to bypass some noise, and this is very this plays very important role in a feedback section. Okay, that we will discuss later. So let's come back how to design this C capacitor means. Thus capacitor resistance, not resistance. That impedance is equals to 1 by 10 of RE. Okay, then the reactance of the capacitor is 1 by 2 C. That's okay. 1 by 10 is a RE, then we can conclude that the C is a 33 microfarad. Okay, then what about these two capacitors? This is this one CC1 and CC2. The two capacitors are coupling capacitors. That means those capacitors avoid DC biasing. If you connect, what happens if you connect directly one stage to another stage? Let's assume there is one more amplifier there. Okay, if you connect them directly, what happens? This DC voltage may affect the next stage, and the previous stage will affect this stage. So that goes to total bias will change, right? So if the bias will change, means if you point change, means your current change, everything change. IC changes means your temperature changes. So that goes away, that goes to thermal control. finally your amplifier gets burned. That's the case happens. This is what about the design. Let's see practical case of this session. Okay? Yeah, sure. Let's come back to the practical way of this is my setup in my instrument setup. This is ABS power supply and this is my digital oscilloscope and this is signal generator. Okay. Oh yeah, my VCC is a 10 volts VCC. Okay. Let's come back to this practical way. Guys, this is the circuit what we rigged up the RC circuit. This is a SL100 NPN transistor. Okay, let's come back to each and every element. These two are the bypass capacitors. Okay, this is it's a DC coupling capacitors, not bypass. Okay, so and then this is a bypass capacitor. Okay, oh, this is a RC what I defined is a 2.2 kilo ohm. Yes, this is R1 is a 22 kilo ohm and this is a 4.7 kilo ohm R2 and this is a 470 ohm RE. Okay, let's first we measure the observation voltages what I defined observation voltages. Okay, and then come back to this and take it as a negative as a reference. Okay, and then sure, first measure V voltage how much it is. Okay, measure this. Our assumption value is a 1 volt, but we are getting is a 0.8 volts. Okay, that's acceptable. Okay, and then VCE is a that's in the terms of 7 point. Okay, VCE means is across collector to emitter, right? So that means that's a 7.25 volts. Okay, maybe it's acceptable. The we are defined is a 5 point something, but it's the coming 7.2 volts. Okay, acceptable. And then this is my VB. That's how we are defined 1 volt, but we are getting a 1.8 volts. Okay, that's acceptable. Biasing voltage. Let's come back to source. It's my source. This source initially I kept it as a 1 kilo hertz, and my voltage is voltage how much? Source I kept it as in 100 volts. 100 hertz. And my voltage is in a dB form. It's a minus 40 dB because my input should be it's in a millivolts. So that may goes to amplify in a volts. That's what amplifier does, right? Let's come back to we will measure in a oscilloscope with scope. Let's measure. That's my V in is a external is my input channel. That's around is a 24 to 28 millivolts, and my output is a 90 millivolts. Okay, and then frequency is a 100 hertz, around 100 hertz. Right. Okay, let's increase my frequency. Okay, let's increase the frequency. We will see what happens. Actually, what's the RC coupled characters? Let's increase as a 200 hertz. We'll see that. Let's say my input is in a 20 millivolts, but my output is a 164 millivolts. That means that's the gain is increasing, right? We will see that. That's in a practical way. Okay, let's increase the frequency. What happens actually? Okay, increase it. It's a 300 hertz. Increase it after 1 kilohertz. We'll see what's the gain. Okay, so 1 kilohertz, for 1 kilohertz I am getting it's around is a 300 millivolts for around is a 20 millivolts. Okay, sure. For 20 millivolts that's in a out of range. We will decrease that's in a 532 millivolts. Okay, and then let's increase in terms of tens, kilohertz. Okay, that will not help you us. Okay, let's say 2 kilohertz, that's the frequency increases. We will see that the frequency increases, right? Increases. What does is RC coupled means is gradually at a lower frequency the gain is gradually increases at a certain frequency it goes up to certain that means threshold frequency the gain almost will be same, right? We can see that that's at a higher frequency that is a 55 kilohertz. We will reduce this. Okay, so we can see that from let's say 1 kilohertz. So 1 kilohertz we are getting is a 540 millivolts. So let's increase in terms, at a 10 kilohertz we are also getting is a 576 millivolts. That means there is no any much change. Let's increase. At 30 kilohertz we can see that there is a 540 millivolts. That means there is no any big out of range change, right? That's almost constant. As you go on increase of frequency, we will see that. See at that's in 100 kilohertz. You can see that that's a 100 kilohertz. It's a 100 kilohertz means it's a very large frequency. We can see that decreases 444 millivolts, right? That's and also take it as a division also for consideration. That's my input is in a 20 millivolts division, my output is in a 100 millivolts division, right? That means my output is in a 4.4 volts, right? Sure. Increase it again, it increases. Okay, in terms of 100 kilohertz, 200 kilohertz. See, we can see that at a 200 kilohertz, there's exactly drop as a 260 millivolts. That's a great amazing of a RC coupled amplifier, right? Yes, sure. See, we can see that as a frequency, higher frequency increases, that's gain is obviously start dip, right? We can see that. So let's increase few more frequency. In terms of, there's a 300 kilohertz. We can see that that's a 176 millivolts. That's at a voltage division 100 millivolts. Okay, as you increase the frequency 1 megahertz, almost it's in a dead condition. You can see that. That's a 24 millivolts of our RC coupled amplifier. That's almost a dead stage. We can see that, right? As you increase the frequency, around it's in 2.9 kilohertz. Whatever we are getting is it's a less than input, right? Sure. That's what the RC coupled amplifier does characters. Guys, this is how the RC coupled amplifier exactly works. We will see the graph and what is the result of this experiment and how do we measure and what is the final our result, what we have to analyze in this concept. We will see that. Let's come back to this practical, what we are analysis in a practical way, that we will compare with the theoretical values. What we got, this VCC is a 10 volts, the small fixed volts there. And then what's the, that's my V, I'm getting almost 0.58 volts and my VB is almost 1.18 volts. That's the design value is, that's the design value 1.7 volts. But I'm getting, that's a VB, my VB is just around 1.58 volts. 1.58 around it. Okay? And then, there's no way of calculating ratios in a practical way. That's absolute. Okay? And then, then what's the response? How we calculate means, how we measure and then consider means, let's take frequency versus your gain. Okay? This is your 20 log AV. This is in a gain, this is a pure frequency. Let's plot it. What you are seeing in a practical way? At a lower frequency, your gain may also is almost a zero. That we are seeing that after a 1 kilowatt or something what we are seeing that there's a gain on motion components at 100 kilowatts or something it gets dropped. And also it's a 3 megawatt, 5 megawatts of a large band, it's almost again excessive. Okay. Then this is our optimum gain. Optimum gain. Okay. This is how much you are getting maximum gain. Okay. And then let's take it's a 3 dB below your gain. Okay. Below your optimum gain dB. Okay. And then here you are getting checking this. Okay, either you are getting some, yeah, okay, and this is your 3 dB of the, okay, this is my FL, lower cutoff frequency, and this is the upper cutoff frequency. After this cutoff frequencies, the gain almost gradually decreases. At the cutoff frequency, this is 3 dB, that means there is a 3 dB cutoff. This is also called is a half power consuming stage. I will explain in depth of this in later my sessions. Okay, this is the band. Okay, how to calculate is your bandwidth? Your bandwidth, right? So BW is equal to FH minus as a FL. That's your bandwidth. That means this much band in between your frequency. That means 100 Hz or something you are getting in a practical way. You will get 100 Hz to 100 kilowatts. That in between whatever your frequency, that almost it amplifies all the frequencies with equal gain. There is no any gain drop. Okay, and then my fourth parameter is the gain product, right? Gain bandwidth product. That's a VM into PW. Almost this factor is constant for any amplifiers. That means that's a gain. If you calculate this point of this gain under your bandwidth, you get same, and this point is called UGB point. UGB point. And this point, what is the UGB point? Is gain, unity gain. Okay, that means this is 20 log 0 means what? 20 log 0 means almost a gain is 1, right? This is a unity gain and the bandwidth is from 0 to this frequency. Okay, and then let's take this frequency and your, it's not 0 exactly, it's an open loop, lower frequency, it's approximately 0. For, we will see that some amplifier has a 5 Hz, 2 Hz, 3 Hz, the lower cutoff frequency and higher gain. This product and this one, gain product, that means this band gain or working gain and almost equal. Okay, this is the concept. Okay, and then this is anything remain. Okay, almost this is the concept of gain. Input versus output, that means you are taking as a input is in a peak to peak, means output should be in a peak to peak only, otherwise it's may becomes error. If you are taking input is in a peak, you should take output is in always in a peak only. If you are taking is in a RMS, you should take is a RMS only. Okay, let's come back to this. Okay, this is my frequency range where I have to take the values. At 50 Hz, we will take a few of the values. We will check whether it's a exact RC coupled characters are coming or not. This is the RC coupled characters, right? We'll check it. What's the lower frequency of that? Okay, let's see that. Oh yeah, that's for 50 Hz we are getting is a input for 20 millivolts. We are getting almost 25. It's the less than. It's a purely less than that. Okay. Oh yeah, that's not in a stable case. Let's assume we are in a 20 millivolts. Okay, then our output is in a 240 millivolts, right? Okay, not 240, it's a 20. Okay, let's take at 100 Hz. We'll see that at 100 Hz my input is almost 20 Hz. And output is reaching to exact 63 to 64, right? Okay. 64. That's enough. 64 millivolts. And then let's increase it to 1 kilohertz. We'll see that what happens. Oh, in between there is a number of points are there. Okay, we will take it for 500 Hz one value. That's in my output is in out of range. Sorry. Okay, that's my output is in that's in that's at a 50 volt division, 50 millivolt division. My output is a 156 millivolts. Yeah. Okay. So let's take its a value at a 50 millivolts division. It's a 50 volts, right? Okay. 180 millivolts at 50 millivolts. Okay, let's take as a 1 kilohertz gain. Let's take it. Yeah, that's a 1 kilohertz. We can see that at the input almost I think to 9, 20 millivolts, but my output is a 8 millivolts at a 50 millivolts division. Okay, so 50 volts division, it's a 280 or 208 millivolts. Okay, for 1 kilohertz. Okay, let's take that's in at the let's take it as a let's shift this frequency. That's in 2 kilohertz we are getting is a almost 220 millivolts at a 50 millivolts division. Okay, and then it's increases to 10 kilohertz. You can see that that's a 220 millivolts, 10 kilohertz. That's a 220 millivolts at a 50 millivolts division. Okay, let's increase us to up to 50 kilohertz. We can see that. So, oh great, it's in a 208 millivolts itself. Okay, great. 208 millivolts for at 50 kilohertz 50 volts division. Okay, let's increase it to 100 kilohertz. We will see that what happens. Oh yeah, 100 kilohertz. At 100 kilohertz, see we can see that that's exactly reducing. That's 174 millivolts, 100 kilohertz. Yeah, that's a 174 millivolts at a 50 millivolts division. So let's increase. This is to mega. Yeah, that's one sec. Yeah, sure. That's the shift. Increases to 500 kilohertz. We can see that it's a it's a 40 millivolts at a 500 kilohertz. There's a large band, so that decreases large gain. So that's a 42 millivolts at a 50 millivolts range. Let's increases to that's a 1 meg. So you can see that almost is less than input. That's that's the input. Oh shit, that's the input is almost 20 kilohertz and output is 68 millivolts at a 1 meg. Oh no. 68 much. Okay. If you increases again a frequency, what happens? We'll see that us almost it's in a dead condition. At 3 megahertz, it's a 14 millivolts. That's in almost it's in a dead condition. You can see that it's almost a dead condition. For input is almost weighing. It's in a 20 millivolts only, but my output is a 12 millivolts. That means it's a less than input. That means there is no absolute any gain of that. Okay, so graph analysis. So I told now it's let's we plot in a semi-log. So I plotted this in a semi-log. My experiment is in. Okay, I plotted in a few of the points, not all the points. You just plot all the points, you will get exact curve. I've taken a few of the points where at a 50 hertz it's a almost 1.2 my gain, and at the at the 100 hertz I am getting a 3.2 dB. At the my maximum gain is at 1 kilohertz I am getting a 5.5 is my maximum gain. Okay, and then where exactly this is a bandwidth, this is a 3 dB gain. Let's we see that. How we see that? As the top end. Okay, that's a higher frequency minus so lower frequency, right? Oh, let's say higher frequency gain, how much is that? 5.5 minus 3.2. It's almost it's in a 2.8 range, right? So okay, it's acceptable. It's a 3 dB gain. Okay, and let's come back to this. It's a 5.5 minus 3. Okay, 3.06. That's obviously in terms of 2.5, right? 2.5. Okay, this is acceptable. This is the gain where it drops. It's a 100 kilohertz is the gain dropping is a 3 dB, and it's a 10 hertz it's a dropping is a 3 dB. Okay, this band from 100 hertz to it's a 100 kilohertz. This band is called my exact amplifier amplifying my frequency. In between frequency there is a sufficient information we can get. Okay, but let's come back to bandwidth. It's a higher frequency pitch. It's 100 kilohertz minus 100 hertz. That's 99 kilohertz my bandwidth. That means it increases, it amplifies from 100 hertz to 100 kilohertz. It's in between any frequency. Its amplifying factor is almost constant. Let's come back to gain bandwidth product. So my maximum gain I am getting is a 5.5 dB. Okay, it's a 99.9 kilohertz. So my bandwidth, the product is a 549.5 is a kilohertz is a dB. Okay, it's obviously fine. Okay, then this is about the semi-log, how to plot a semi-log graph and all those things. Guys, this is all about the frequency response of a RC coupled amplifier. Okay, in my next session video, I'm gonna explain you what the characteristics of this amplifier. That means the input characters, output characters. That means the gain. Everything I'll discuss in my next session video. Please watch it and thank you for watching.